Hey, how are you? I'm Christopher Pies, and welcome to my first video in what I hope will be a series of videos that talks about dev environment and CI/CD pipeline from a developer's perspective, some of the common problems we run into, and solutions for them. The first thing I want to talk about is a mismatch between environments. I've made a bit of a quick chart over here on my other monitor to depict the common scenario that I've found. 9 times out of 10, things seem to be set up this way, where we have a number of developers over here on the left side, and then, they're pushing code to a Git repository. Maybe that sits in GitHub or Bitbucket or, any number of different source control systems. And whenever they push code, it's going to kick off an automated build and a running of the unit test. And down here on this build machine, it's going to get the code from the Git repository. It's going to compile it and link it. And then it's going to run the unit tests and spit out a report. And available on some web interface to the developers, they can see if the check-in made the build pass or fail. Down here, we have an artifact repository in some places where the outputs from the build are stored. Perhaps some third-party libraries have been brought in, pre-built, and those are on the artifact repository if you're lucky. From there, the QA team can pull certain builds which will be tagged, and typically it'll be some version number that they're going to release, and QA will be testing that. And then, of course, in the end, you want to deploy to your customer. And take note, between all of these, we have different operating systems, maybe different versions, different hardware that they're running the system on. As a result, the software is going to run differently on one of these machines compared to the other, and the developer might not be able to reproduce very easily something that the customer's reporting. Likewise, QA might have a complaint and the developers don't know what they're talking about because they're not experiencing it in their day-to-day. And this is because there's so many different factors at play here in these different environments that are going to cause the software to behave differently. And some of them aren't as obvious. Consider, the implementation of a networking library like Boost ASIO. That's going to be implemented differently on a Windows machine than a Linux machine under the covers. And the developer might not realize that because it's abstracted away and they're dealing with the same interface no matter where they are. The only way they would know is if they're very familiar with Boost ASIO and they've read through the documentation and they were thorough, but that's not always the case. But irregardless, that software is going to behave differently on one machine to the next. Another example would be the way timers are implemented. That's going to be different depending on the operating system. Many libraries implement them in different ways. The precision is going to be different in different environments, and depending if the machine is under load, software is going to behave differently. You may be thinking to yourself, well, Chris, this is all really obvious. I don't need a video for you to tell me to match environments. Obviously, that's important. And yeah, I agree. I haven't really come across many people that don't think it's a good idea, but I don't think that this concept is at the forefront of people's minds all throughout the organization, because I've worked in countless organizations where all the environments are different. And there's different reasons for that. It could be, the developer's preference. They like a certain set of tools. They might have forgot to get particular versions of different libraries. A big one is if I go to higher management and I ask them, well, what is the operating system that we're officially supporting? What is the customer using? They might not want to limit themselves by declaring an official operating system, or even 2 or 3. That a lot of the times they just want to support everything. And of course, as a developer, we look at that and say, well, we've got a team of 5 or 8 or whatever the number, the head count is, and supporting every operating system in the universe is just not going to be possible, at least not very thoroughly. So in that situation, you would ask, well, what is the largest customer base? What's the biggest piece of the pie? And let's target that. Another thing a lot of people don't consider, except when they're a new hire, is the onboarding process and mentoring in general. The difficulty that's created by this scenario, let's say, for example, developer number 2 is our new hire, and they just come on board. They're all excited. They want to get into the code. They're hoping to see if it's maintainable and get their feet wet, start understanding things. And we've got developer number 1 who's been here, since the beginning. Maybe developer number 1 has a bash script on their machine and they set up a bunch of environment variables, and they can switch back and forth depending which operating system that they're targeting. And they tell that new hire, go grab my bash script and just run that, and it's going to set everything up for you, and I'll walk you through it. And they spend a couple hours and they go over that bash script, and developer number 2 is halfway through their onboarding process. But then they get stuck and it's Thursday, developer number 1's not available anymore. So the new hire goes to this developer number 3. Hey, they're a senior engineer. They can probably help me out. And they have a video chat. Well, developer number 3 takes a look and what are you doing? No, I'm running this bash script that's setting the environment variables because so-and-so told me that's the way to do it. And developer number 3 is, I can't help you. I'm completely lost. I don't know what's going on here. Things aren't in the directories where I put them, and your environment variables are different. And I don't know. We're going to have to wait for developer number 1. So this new hire is stuck. And oftentimes, what they're going to do is drop what they were doing over here and all the progress they made and say, well, they're not available anymore. Let me mimic what you're doing and start all over again from scratch. And a number of days or weeks is spent just getting things up and running to the point that they can go get code and do their first build. And I think that can be completely avoided. How do we solve the problem? Well, we can use containers and virtual machines. Surely by now you've heard of Docker and containers, and you've probably heard or used a VM. I first heard about Docker back in 2018, I want to say, but I never really paid too much attention. Now it's become pretty much an integral part of my development process. Just take these videos that I'm making, for example, on my channel. I plan to do some C++ tutorials and maybe have a kind of an online code walkthrough, and then I can offer people a Docker file and say, here's the Docker file with the environment that I'm going to use, and it's got all the tools that I'm showing on screen and all the libraries that I'm working with, maybe my own libraries even. Everything's ready to go. So all someone has to do is download that file, build the image, and make a container, and they're all set. There might be a little bit of instructions on how to connect an IDE to the container and to get familiar with Docker, but I guarantee it's going to be much simpler than, that typical document that we get in our email that's, hey, go check out the Confluence page and here's 5,000 commands that you need to run and a bunch of different addresses and libraries you need to install and all the paths you need to memorize. With this, we all have the same environment. We just go to Git repository, get that Docker file. All 3 of these developers, they can be on any machine that they like with any operating system. They can have their own tools, customize things how they want. But when it comes time to collaborate or fix a bug and reproduce it, they can turn to our official development environment, crank up that Docker container, attach the IDE to it, and they're good to go. And the same down here, QA is running whatever operating system we're targeting. Maybe we have multiple customers, multiple operating systems. Well, we can also have multiple containers, and a developer can just easily switch between different containers for the OS that they're targeting. So using a container might not always be a viable option. There's proprietary operating systems out there. Sometimes you're targeting a piece of hardware. You might have a physical piece of hardware on your desk that you're uploading to as you code, and you're not going to be able to make a Docker container out of that. There's a scenario I'm reminded of when I worked for a particular organization. We were targeting, I think it was IBM Power PC. And what they did was make this one machine that was an actual Power PC and enable all the developers to connect to it. And we'd all have different accounts. I want to say maybe that's okay as a very last resort, but there was a lot of problems. It was probably worse than the scenario that we had before if we all worked on our individual machines, because now this is akin to you coming to work in the morning and your coworker has logged on to your machine and uninstalled something or installed new files and affected the entire system, or maybe deleted a directory. Everybody's able to affect one another. There might be ways to isolate those accounts so that they don't have an impact on each other, but then you're going to take up more resources and have your own copies of files and stuff like that. And usually in this kind of scenario, the developers are going to have like admin privileges and they're going to install and uninstall stuff willy-nilly, probably not coordinate with each other. So it was very complicated, and there's a lot of trouble that was run into that I wish could have been avoided, but I personally can't come up with a solution on, how are we going to all target Power PC and not step on each other's toes and do something like a VM or containerized solution. I don't know if IBM offers some kind of image that you could run on a VM on a different architecture, but I don't think so in the very limiting Google that I did. Let me know, leave me a comment. Let me know if you know a way to tackle that problem. Another problem I ran into with containers is that if you want to run a GUI, I really think that containers are intended for something that has no GUI, something that might just run as a microservice in the background. There is one project I was on where we were using the Qt library, and we had a GUI that we needed to interact with, even during development, needed to interact with it so that we could debug and see the effects of the different states of the system. And tried to make that run in a Docker container using X forwarding, and you can do some X forwarding, but it wasn't consistent. It worked for some people, it didn't work for others. There was a lot of different configuration changes that you had to make, and depending, what these developers had on their laptops, on their physical machine, the configuration changes that we had to make were different. Never did really get it to work consistently. If I had to do it again, I'd probably use a VM. However, there's no one solution fits all scenarios. There's a lot of factors that go into it, and you have to kind of analyze what you're working with and do a little trial and error. The VMs, a sticking point there could be, it takes a lot of system resources to run a VM. And if your organization is giving their developers laptops with, 8 gigs of memory on it and trying to skate by with the very minimum, it's probably not going to run a VM very well. And then you're going to run into issues where things aren't working as expected. There's crashes and people are getting frustrated and they're losing time. So that's something you would really want to plan for up front is, talk to management, talk to DevOps. Hey, we like to use VMs. We think that's going to help our process. Explain why, that the hours that go into not having a consistent environment, and see if they'll give you a budget for it, what that budget is, and what you can get. And then again, it's going to be a little trial and error. Get one machine, put a VM on it, see if it works for your uses. One application that you're developing could be much different than another. I have no idea, what the constraints are on your particular project. But, you can do a little research, take a little time, see if it works for you. I intend on making a video in the future that'll dive more into the details of setting up the Docker container, putting your tools on there, walk through the Docker file, show connecting an IDE and actually stepping through code and debugging and all those kinds of details. This video is just supposed to be more of a high-level introductory video that doesn't get into the nitty-gritty details of how to do all these things, but just talks about why we would want to do those things. So I think this is where other content creators point to a empty space and plug in a link later on to a future video. So I'll do that too. If you don't see one, look down in the video description. Might have put a playlist there, or might have a link there. If none of the above, then sorry, I just didn't get around to it. The next topic I wanted to talk about is the active vendoring code. And if you've never heard of that before, it's referring to this situation that I have on the screen here, where maybe our project has a bunch of dependencies, or those dependencies have dependencies. And what is happening is that the developer is going to hit build, and as part of that build process, it's going to go and fetch projects from the internet, usually just their source code. Take the Boost library, for example. If we're pulling the entire Boost framework, I should say all the Boost libraries, there's multiple, it's a really big collection that takes sometimes an hour or 2 hours, depending on the hardware, to build everything. So if you're pulling all that source code and building it every time, your build time is just going to balloon up, both on the development machine and then the build machine as well, because the build machine is parsing the same files that control how things are being built. In C++, oftentimes we'll be using CMake. There's other things that could be in use. If you're in a Windows environment, you're probably using some MS Build. There's all manner of different systems in place. But if you happen to be using CMake, you can look and you might see this external project command, or you might see this fetch content command. And in that command, you'll see links that go out to the internet. And this is referring to some Get repository that's just public. And we're pulling some third-party library, a particular version of it, down, and that's going to get built. Sometimes DevOps might get wise to that, and some of the libraries will be pre-built, and you'll have those pre-built binaries over here on an artifact repository, and then the developer might be able to grab those and install them on their machine. But notice in this diagram, there is no direct connection between this artifact repository and the developer's box. What I've seen a lot of times is maybe those pre-built libraries get checked into the Get repository, and then you're taking up space that shouldn't be taken up. The Get repository is not for third-party libraries. Sometimes the code for the third-party library goes into the Get repository. Take Rapid JSON, for example. In their documentation, they have what they call the amalgamated source files, and it's like one header and one source file. So people will just take that and put it directly into the repository, maybe along with a bunch of other code. It could be like in your utilities library, or, for example, I've seen it just laying there. So your Get repository is just blowing up because there's a bunch of third-party source code in there. So you'll have to forgive me, I already updated my diagram to get into the next topic, but there was one more thing I wanted to talk about, and that is that sometimes the developers will build some of these larger dependencies themselves, like Boost or Qt or whatever, and they go and they get the source code for it, they pull it themselves, and they build it on their local box, and then they'll have those binaries sitting in a directory somewhere on their machine. And whenever they build the project, they're going to point to some path. Then you'll find yourself in that situation that we talked about earlier in this video, where all the development environments are different because they're using different versions of the libraries. Maybe Joe decided, hey, I'm going to use Boost 1.7.0, and he talked to a couple other developers about it, but Sally wasn't involved and she didn't know. She hasn't updated her Boost build on her local machine since 1.6.5. And then she's finding herself in the situation where the system's not behaving as she expects and goes to the senior developers. Hey, what's going on? Did something change? All of a sudden X is broken and I don't know why. All my source code is up to date. What's going on? Oh, Sally, we are using Boost 170 now. You didn't get the memo. And it's just really bad to rely on that word of mouth, verbal communication for changes in the project. Enter the package manager, which that's the solution I have on screen. Typically, a package manager will work off of some kind of recipe. I'm used to using Conan, so I'm using the term recipe here. There's other package managers. VC package exists. When I first heard about VC packages, way a long time ago, that was only going to work in a Windows environment, and we were using Visual Studio at the time. I've heard that VC package is now cross-platform, and it's open source, so that's another option. But I'm familiar with Conan, so I'm going to talk about that, and I use the term recipes. But you would specify in a file that goes into your source control, this target is dependent on, and you list your dependencies along with the architecture, the version, whether it's static or dynamic linking, or if you're on Linux, to be static or shared library. And you specify all these things, so you can have different copies of pre-built binaries. I could have Boost that's built for static linking that's targeting x86, and then I could have another copy of Boost that is x64 and it's version 170, and it's for linking as a shared library. And you'll have a repository for all these things. So let me step through how this would work. So developer gets pulls the repo. The source code has a recipe file for the library he's trying to build. Let's call that library database interface. And it's got a dependency on some JSON library. So he specifies, hey, I need rapid JSON for x64. I'm targeting, this flavor of Linux. Go get it for me. So he's got a package manager on his machine. Sorry, I didn't depict the boundaries of, this is a machine for the developer and a package manager combined. And as it's building, that gets parsed, and the package manager knows that, hey, we need that dependency, and I'm not seeing it in the local cache. So it's going to go out and get it from whatever is specified as the remote repository. So in the optimal situation, we've updated the package manager to point to an artifact repo that's in the organization. When you first install a package manager, they're going to go out in the internet and hit a repository, some kind of central, like Conan central repo, and pull the dependency from there that you're looking at. And if it's something that's popular that a lot of developers use, it'll be on there and it'll pull it down for you. But you'd like to have it set up to where everything's internal to the organization, just minimize security risk, and you're pulling it from your own repo, and that's set up to have all your dependencies, and that way you have your checklist of what's on there, and you can pull it whenever you want. And this is great if you're targeting different operating systems, different architectures. You never have to build these things over and over as you're switching environments back and forth. You just say, build my code, and it's going to go get those pre-built libraries for you. If you've worked with other languages, you've probably worked with a package manager. In Java environment, they have Maven, and that's so integral to using Java that the integration is built right into the IDE that you're using a lot of times. And if you buy a book on Java, they're probably going to talk about Maven. It just goes hand in hand. If you're using C#, you're probably using NuGet. If you're a Python developer, you're using pip on a daily basis. It just strikes me as odd why I go to all these organizations where I'm working on C++ with other people, and nobody really mentions a package manager. It's never brought up in conversation. I guess maybe everyone just assumes that they don't exist for C++. I don't know. I could speculate as to the reason, but that's a exercise in futility. But they do exist. I'm here to tell you, we have package managers in C++, and by golly, it will make everyone's life a whole lot better if we start using them. I just want to mention before we move on to the next topic that package manager is not only for third-party libraries, but you can also build the libraries that are part of your project and use the package manager to go get them. So you don't have to build this big monolithic repo that contains everything in the whole system every time that you're doing an update to some piece that's just in one executable or one library, or maybe you're updating a unit test. Well, you don't have to build the entire world every time. That'll provide the segue into the next topic I want to talk about, which is the monolithic repo. I haven't admittedly talked to a lot of people about pros and cons of this, but I am of the opinion that we should stop having a monolithic repo. And if you're not following what I'm talking about, I tried to whip up just a quick, simple demonstration of what I'm talking about by just making a project in VS Code real quick. By no means is this as monolithic and huge as it really is out there in the world. I've seen repositories that just have 30 or 40 or 50 folders, and each one of those is a different library that has subfolders, and maybe it drills down 8 levels. I just made up some stuff. This is just a fictionist project. You might see some C++ projects that you work on has a common library, or maybe it has a utility library where they just put code that's probably going to be used all over the place. Maybe someone came up with some template that they use over and over, or a handy dandy macro that they're going to use all throughout the code, or commonly I'll see someone make their own thread class. We'll make a whole separate video about things like that, and redoing string from the STL because they didn't like the string implementation, and things like that might fall in. Anyway, I'm getting sidetracked. So you might have other libraries, like maybe our project is interfacing with a database, or maybe we're talking over gRPC, so we have separate libraries for that. Maybe we have a GUI component, and here's where we specify all the different GUI controls and how they work. And maybe the GUI is calling the state machine, and the state machine is the actual executable. So we've got this one executable, and we've got these 1, 2, 3, 4, 5, 6, 7 libraries. And typically, each one of these is going to have subdirectories and different things in there. Maybe they'll have a test folder where they'll have their unit tests. Maybe they'll have an integration test folder, and there's different automated tests for integration testing there. There might be documentation folders up at the root or in each individual folder. And the complexity level is it's endless. It can go on and on, be as complex as you want to make it. But rather than do this, given that we have a package manager, why not just make a repo per library? As far as I know, there's no limits in GitHub or Bitbucket or anything that you're using for your source control as to how many repos you can make. You could make one that just contains one library. And in that repo, you have the documentation for that library, you have the unit tests for that library, and then you have the source code and include files for that library itself, and the package manager file, which dictates how we're going to make a package out of that library and any dependencies that it needs. And it's all by itself. And that way, if I get a ticket and I need to work on that library, I don't need to go download all the source code for the entire organization and sit there for 2 or 3 hours and build the entire thing. I'm just going to build my library. And, if I'm a thorough developer, maybe I have it set up where I can go pull all of the artifacts that are already built for me out of the artifact repository. And they'll be there because we're using a package manager, and I could go pull them down. I could put together the whole system and do a test run. And some people might be thinking, well, I need to pull all of the source code and build it all and have all my libraries freshly built so that I can step through with the debugger. Maybe they start up here in the state machine, there's some bug. That state machine calls, the DB interface. They want to go in there and they want to see the state of all the variables and which thread is running, and maybe they have to delve all the way down. And maybe the DB interface is then in turn calling utility, and at the very bottom is that thread class that I mentioned that somebody made up. And they want to step into that. Well, you don't necessarily need to build all that from scratch. If you have the version numbers and the recipes and the package manager, you just go get the source code for that version. You don't have to build it. When you build your packages, you can have debug versions with the symbol files, and you just got to point to your source and debug that way. So that you still save the hours of building that source code and machine code from scratch every time. Even if you do want to go pull those dependency libraries and build them from source code just to be sure that things are in sync, because I understand that. I've been in situations where I'm debugging code and nothing's making sense. It should be working. Something really odd is happening here, so I just want to make sure I'm in sync. So I built it from scratch. Even in that situation, you probably, I hope, don't have this situation where every library is dependent on every other library. You should be able to go into the system somewhere and only take some subset. Let's say we're in the DB interface. Hopefully, it's only dependent on a couple, and we have, say, utility and state machine in there. Now, maybe the state machine at the top really is dependent on everything, and if that's the case, then go for it, go pull it. But you have the option, and at least you're not doing that as part of your development process every single time. You can do it only when you need to do it. So it's going to speed things up. When you have everything together, if it was just the common library, I'm just going to have a couple folders. If I open that up, maybe I got my test in there. I'll have a CMake file. I'll have the CMake for the common, and I got a couple source files, a couple include files, and it's real easy to keep track of what I'm working on, what changes I did. Someone might argue that, well, I need all the source code because if I change one thing in one library, it's going to have an effect on these other ones, and I got to update those as I'm making the changes. And I'd argue, well, a library should have a clear, well-defined and understood interface, and everyone in the organization should be familiar with that interface. It should be part of the documentation, and all the libraries and executables that are dependent on that library should be familiar with that interface. They shouldn't be looking into the internals. I have seen, I've seen some things. Some libraries that are just chock full of classes where everything is a friend of everything else, and they're all including the headers from all the other libraries, and the whole thing is just, it might as well not even be C++ and not have classes and objects at all. But, if we're doing things right, or at least we're striving to, let's make clear defined interfaces for our libraries and keep things separated. And that way, we can do this whole system where a library is a black box. That's what they taught us in school, program black boxes. And we can check them in, test them individually, and use our package manager to keep track of the versions. And if we come across a scenario where that interface is going to change, well, we increment the version number. And now it's an official thing. It's not something that just slips by and nobody notices it. We increment the version number. Hey, the interface changed. I can update the documentation. I can go and mention it in the Scrum the next day. Hey, we got a new version of the interface. Is now a good time to go and update everyone who's calling that. Let's identify those things. And, again, we have the documentation. We don't have to spend hours and hours crawling through code and saying, who's dependent on this library? We have right there that recipe file, and we know where to look at it, and it's real simple to read. Granted, we could scour the CMake files and see, what's linking what, but it takes a little bit more time than just having it in that recipe file. I'll show you in the video when we actually demo the package manager. The last topic I want to talk about in this video is deterministic unit testing. As we mentioned in the beginning of the video, if you've been a software developer for a while, you probably run into that scenario where the unit test just randomly fails. You think you're done your ticket, you've checked out the code, made your update, pushed it, automated build kicked off, unit test failed. You run it again, it passes. 3 hours later, unit test fails. Just no idea why, what's going on, just random failures. Maybe it fails on one of your coworkers' boxes and it doesn't fail on your machine or the build machine. Just random failure in different environments, or maybe even in your own. Well, that test doesn't have a deterministic result if the results are different. That's what we're talking about when we're talking about deterministic testing. So what causes these random failures? Well, there could be a lot of different things, some of them obvious and some of them not so obvious. It just comes with experience after having dealt with them over and over that you begin to identify them. A big one is using a resource. Consider someone who put a network client and network server in a unit test. Maybe that network server is on a remote machine, or maybe it's local. Either way, there could be permission issues. The host could be unresolvable. Network could be flooded. There could be a firewall. All those things would cause that unit test to fail. And we really don't want to test the network. That's where we would go into the integration test or the system test to test the network. The build machine doesn't have the environment that we're going to have in production. You're going to have all kinds of traffic from other teams trying to queue up their builds, and who knows what's going on there. Firewalls are all over the place. It's going to be completely different than your production environment. So you don't want to test the network resource. You want to test, does my code react to the responses that I get over the network, and the layers that are built on top of whatever's sending over the network. Maybe you have layers yourself. Maybe you have an HTTP client and you went and implemented WebSockets yourself on top of that, or the Stomp protocol or whatever. You want to test that code. Another example of a resource would be connecting to a database. Maybe that database isn't available. Maybe someone changed the state. The table has updated values in the rows that you're looking at in your test. Could be permission issues, all kinds of things. So it'd be much better to supply the test with a set of data that's the same every time you run the unit test, guaranteed, and you know what the result's going to be, and you can go and program your unit test that way. One that's harder to identify is multi-threading issues. You could have deadlocks. The thread could run faster depending on the load. You might have different hardware resources available. That one's a little bit more tricky to diagnose. Another one would be timers. Timers, all the time dealing with timers and tests. It's a mess. The timer might not have the precision that the developer was expecting on one machine compared to the next. Someone might have not even considered precision at all. For instance, littered the code with sleep and just come up with arbitrary numbers. I just want to sleep 5 seconds because I know the code breaks if I don't. Well, please don't do that. It'd be much better to identify the condition. What am I waiting on? Am I waiting on another thread to complete? Am I waiting for my queue to fill up so that there's data to pop off the queue? Use condition variables in your code, identify what you're waiting on, and wait on that condition. When that condition happens, the code right away goes. Also consider intervals with timers, the polling. If in production, maybe you're waiting for a ridiculous amount of time, like 30 seconds to ping some server and see if they're still there because you haven't got a response. And then a developer comes along, I'm going to put that in a unit test. Well, do you really want the build machine to sit there idle for 30 seconds on all the unit tests? Maybe you have 12 of them, and so you're taking up a whole extra 6 minutes just because that timer normally waits for 30 seconds. Well, what if you could derive from that timer, change the implementation of it, provide a method that says fire, and have that timer trigger immediately? Well, you can, and that's where mocks come in. You can use mocks and fakes to change your unit tests so that they have deterministic results. And you can skip over the scenario where you're using a network resource. Instead, you can provide your unit test with the expected responses or the unexpected responses and have a deterministic result on how your code is going to react. And that is what you want to test. Now, to use mocks, to make fakes, it's going to require some polymorphism. You're going to have to use inheritance. When we study C++, we've all went over what is object-oriented programming. We know how to make classes. We know what virtual methods are, all that stuff and how it works. But it seems you get into the code base, you don't really see abstract classes all that often. You don't see people making interfaces, at least not in my experience. Most organizations, people just go in there where, granted, everyone's usually in a rush. There's reasons, there's deadlines, there's pressure. So most people just dive in and make the concrete class. But in order to employ this this unit testing methodology where we're going to go and make mocks and we're going to have deterministic tests, we're going to have to take the time to go and make proper C++ interfaces using the abstract classes. And then it gets a little bit more complicated. A lot of people are a little intimidated by this phrase, but I like to do dependency injection in the test. If we make the code in production such that we're taking interfaces rather than the concrete classes, we can set those interfaces to point to our desired implementation. So you're using the production concrete class in production, and in the unit test, you're setting a pointer to that interface to the mock implementation, and you're using that. And that way you can pass it around to the different methods that call for it, while still calling the methods that you provided on the mock, or checking conditions in the state of the object. I don't want to delve into code examples and go too far into it, because this is another one where I intend to make another video. I will give kind of a verbal description. Take our timer example. Boy, Chris loves to talk about timers. Yeah, I'm sorry. But consider you have some class in your project that uses a timer and it's pulling on an interval. Say it's your network client, pulls on an interval, and every second it sends a ping and it expects a pong. And you want to unit test that. Well, now instead of having the timer as a member variable in your network client class, and then having the network client in the body of the constructor creating the timer and setting the interval, the network client class in its constructor takes a timer as a parameter, an interface for a timer as a parameter, and it says, give me the timer. I don't know what your concrete implementation is, but because it adheres to this interface, I know how to use it, so please give me one. And in the production code, you just go make the same old timer outside of the class. And then when you're creating the network client, you pass it in the network client's constructor, and you're setting which timer am I going to use. Back in the unit test, rather than using that timer that has that interval set to a second in this case, you're passing the mock. And the mock might still have methods to set the interval, but it doesn't do anything because it's the mock for the unit test. You don't want to wait a second in your unit test. You want to fire the timer, and you want to test, does that ping go out in my network client? So your unit test gets real easy then. You have that mock timer you created outside the class in the beginning of the test. You pass it into the network client and you say, fire. Now you can go into the network client and see, did it actually try to do the ping? Now, again, you don't want to use the network resource, so maybe you have, other mocks that you've also given the network client. You don't actually go over the network, but that's complication we'll leave out of the example. I hope that kind of clears up what dependency injection is. It's simply take the responsibility of creating the dependency in the class, move it outside the class, pass as an interface the dependency to the constructor of the class. You could also make methods that take the dependencies, and it doesn't necessarily have to be the constructor, but I call this constructor-based dependency injection. I apologize, what I just described is technically a fake, and I referred to it as a mock. I tend to refer to both mocks and fakes as mocks. I'll go put a text block back there and edit. Anywho, so that's a fake because you're bypassing an expensive operation, in this case, the waiting for the poll, the interval to go by. What a mock will provide for you is that you can inspect the state of the object, how it was called, what was called, the parameters that were passed. So go back to that network client example. Let's suppose that our network client is just layers above an actual network client that goes over HTTP. And we're using that from some third-party library. Well, in that case, we probably have to make an interface for that third-party library HTTP client and define the methods that we expect to be called, and then go make the concrete implementation in production point to a wrapper of that third-party HTTP client. And then in our unit test, we make the mock HTTP client, give it to the constructor of our network client. And now when we expect that ping to occur, we can test, did the HTTP client, the mock object that's representing the third-party library HTTP client, did it get a call to send a message, and what were its contents? Did it match a ping message? So you can go and say, did this method get called once? What was the parameter? And get the data and compare it. And then your unit test will tell you, yes, you tried to ping and the message matched, but you've never gone over the actual network. So that's how a mock object works. And they're extremely useful in unit tests, albeit a little complicated to set up and a little intimidating for sure. So I see I've run about 50 minutes, which is much longer than I intended for an introduction video. Probably delved a little bit too far into details, but anywho, thank you for sticking it out with me. I hope that any of this information was useful, and we'll see you again in some future videos.